Welcome to the Listen Up podcast, where we explore hearing loss, communication, connections, and health.
Hi, everybody. It's Dr. Mark Sims here. I'm the host of the Listen Up podcast, where I feature top leaders in healthcare. Past guests include Dr. Drew Dundas and Dr. Rodney Perkins of EarLens. This episode is brought to you by Arizona Hearing Center. I help patients to effectively treat their hearing loss so that they can connect better with their friends and family and remain independent. The reason I'm so passionate about helping patients is because I lost my brother Robbie twice, first to his hearing loss from radiation from his brain tumor, and then again when he passed away. I only care for ears. I'm the ear of ENT who's performed over 10,000 ear surgeries over the past 20 years. I'm the founder of Arizona Hearing Center. I'm the author of Listen Up. Go to listenuphearing.com to learn more about the book. And go to www.azhear.com and contact us with any questions or email us for support. Today, I've got a great guest. It's Dr. Jeff Crukley. He has a PhD in Health and Rehabilitative Sciences from Western University. He's worked as a researcher in both academics and industry in audiology. Now, Dr. Crukley's passion and working area is as a data scientist. He helps people analyze data and represent it. I'm really excited to have you here, Dr. Crukley. Welcome to the show, Jeff.
Thank you very much.
So tell me your path into hearing sciences. I'm always fascinated how people ended up in where they are now in terms of audiology and then into data science.
It's my path is a long and circuitous one. I first learned of audiology during my undergraduate, which was in biology and psychology. I did some volunteer hours in a hospital-based audiology clinic and thought that it looked like a very interesting field. After being out of school and working in a couple of biotech companies and some other research contexts, I went back to school for my master's in audiology. And I did a combined program of clinical training and research training. And the research side of things really caught my interest. My master's work was looking at localization ability with and without hearing aids. And from there, I went on to pursue my PhD in hearing science. And that was particularly interesting. I was looking at the ability to best accommodate children with hearing loss in school-based environments. And so that work focused on not only treatment options through digital signal processing, but also through assessment options. And I built out my own mobile assessment lab. And so I did all of the research and speech testing and loudness discomfort levels. I did all of that within the schools themselves in real classrooms, as well as looked at, soundscapes of what things look like from an auditory perspective for kids, and particularly for kids with hearing loss over the course of school days. And I spent time in daycares, elementary schools, and high schools over a period of several months, just kind of tracking the ability to assess and then, best provide support for kids and their listening needs where they spend most of their time, which is in school. And then after that work, I went on to do a postdoctoral fellowship in medical biophysics. And in that context, I was looking at auditory fMRI in a very different segment of the population. So I was looking at doing auditory cortical imaging for premature babies and looking at developing some ability to look at long-term developmental trajectories based on patterns to auditory stimuli through fMRI. And that was fascinating work and was kind of my first real introduction to data processing, number crunching, and some relatively complicated statistical analysis. And from there, I went on to industry, where I worked in a research capacity for, close to a decade. And that is where I really found the need for flexible and intuitive and out-of-the-box ways of analyzing experimental data. I find that, or did find at least, when looking at results of experiments or trying to design them in an industry context, we were particularly curious about performance outside of a constrained lab environment. So how are things going to look for real individuals in a real world context? And that's just not something that is easy to assess with kind of the typical approach to statistics like t-tests and things like that. You need to be a little bit more flexible. And that's what led me to where I am now, which is focusing primarily on, really custom coded, custom created models that are both evaluative and generative. So what I do now through analysis is understand what happened in a study, but my models also work in the opposite direction so that I can use them to predict and create data. So they work as data simulators as well as data analyzers. And the flexibility there has proven to be really valuable, both for understanding research data in some contexts, as well as providing kind of a backbone for development support in tech companies.
Yeah, that's really great stuff. I mean, the stuff that comes to mind really clinically, and that's what I think you're getting at are two things. One is I'm not sure people realize how much background noise there is in schools, and it sounds like you're trying to keep track. Your PhD looked at that. I mean, in the context of, you could speak to that, I should say. And then the other thing is I think what you're getting at is what many patients complain. Well, I hear great when I'm in the audiology booth, but then when I go out in the real world, I don't hear nearly as well as I do when I'm in the office, right? And so
exactly.
That's what you're trying to model is real world situations as compared to that. And just touching on your PhD thesis, can you speak to I mean, I always say to patients, parents, the hardest listening environment for hearing impaired children is the school environment. How hard is it? I mean, can you just speak to that? I know it's kind of just touching on your PhD, but how hard?
It's very challenging. But what was really interesting about the work is that it's not easy for any kids, because there are published guidelines for kind of where the levels of background and ambient noise should be, the kind of sound reinforcement or suppression that should be present in classrooms. And through my measurements, I did full acoustic measurements in a large portion of rooms in a number of different schools, and almost none of them met that criteria.
What is that criteria?
The criteria is well, I mean, ASHA recommends that there is a signal to noise ratio for children of plus 15 dB. That means the teacher's voice should be 15 decibels higher than the background noise. And that was almost never achieved. Background noise levels, and this is where I redefined things and kind of coined the term non-quiet listening. I think people think about speech and noise as, trying to speak, in front of an air conditioner or in a busy restaurant or busy bar. And, when things get up into, shouted level speech or louder than that at around maybe 80 dB SPL or something like that. But what I found was, it's almost never quiet. So although the overall levels might be where you would say average level speech is happening at around 65 dB SPL, it's not a single speech source. So there are multiple sources contributing to that overall level, and disentangling the information you want from the information you don't want is challenging for many
Normal
kids,
hearing kids, right?
Especially, kids with a hearing impairment. Hearing aids are still not quite at the point where they know what you're trying to listen to. So we can identify what is speech and what is not speech, but we can't yet really do a great job of identifying which speech you want to hear and which speech you don't. So it becomes very challenging.
Yeah, that's a lot of brain work to filter out what you want to hear, what voice you want to hear as compared to not to. And then when you're not getting the signal well, that makes it even more difficult. Yeah. That's fascinating stuff. Yeah, I mean, I'll just share with you, we were talking in the pre-interview about dating ourselves. All of the schools I went to had hard tile floors. And all the schools my children go to have carpeting. So they did learn something in terms of decreasing the background noise.
Yeah, I mean, some of the things we can do are very cost efficient. Carpet, mats, curtains on the windows, drop ceilings are good. Even simple things like, some memory foam tucked in the corners to kind of stop some of those early reflections. Just to kind of just to suppress the reverb a little bit. The signals of interest get smeared out really quickly when a bunch of children start speaking at the same time.
Yeah, and that's why, as they call it in the teaching world, classroom control is so important for the teachers, right?
Absolutely.
Yeah, that's great stuff, and really great work because it's highly impactful on actually our normal hearing kids and our regular kids. So one of the things I was talking to another guest about, which I think is an interesting thing, is looking at the audiogram. We typically just talk to people about their loss or how much we have to turn up the volume on the scale of on the dB scale. The thing that it is it's a logarithmic scale. And so, being that you're a data scientist, I'm putting you on the spot to kind of help the listeners to understand what that means in terms of, sometimes you say, well, you've gone from 10 to 20 dB loss. That's not a big deal, but I'm not sure people really understand the magnitude of those types of changes across the logarithmic scale. Can you speak to that?
I can. It's an interesting time to be talking about the log scale as we're hopefully coming out of the the COVID-19 pandemic, where there was a lot of talk of flattening the curve. Of course, the curve we were trying to flatten was on the logarithmic scale. And even when the logarithmic scale is flat, the linear scale, we're still seeing more cases every day. So while the growth slows, it's still growing. And I think we see the same kind of contrast in thinking about increase in decibel-based thresholds, which are on that log scale. And we try to compare that to the clinical audiogram, which is at least presented as a linear scale. And, we have our categories of mild to moderately severe. And it seems like there's this linear relationship. But I think what is difficult to grasp is when we typically look at a graph on a usual scale, on the axis, one tick mark to the next tick mark is additive. So, 1 plus a 1 unit increase gives you the next tick mark, which is 2. That's the linear scale. On the log scale, it's not additive, it's multiplicative. And so, although they are still single tick marks, you're multiplying by 10 between each tick mark. So the first tick mark is 1, the next is 10, the next is 100. So you see this exponential growth. And so moving one tick mark on the scale actually implies a more significant reduction in sensitivity than might be depicted when we think of that audiogram on that 5 dB linear scale. The impact to sensitivity is actually multiplicative and significantly greater than we're very easily able to convey on that graph itself. And so that's where I think things get a little bit challenging to understand. But I think the framing and kind of color coding or shading in mild to moderately severe and orienting patients to those categories is a helpful thing for them to understand, what their expectations should likely be. And I think setting expectations is a very important thing early in the hearing aids or early in the hearing loss experience.
Yeah, and so correct me if I'm wrong, but what you're telling me is that the further down you go, the bigger the change each 1 dB is. Is that correct?
Absolutely. Yeah, it's because of that multiplicative effect. The amount grows between each subsequent tick mark, and so the spacing looks similar, but that's more as a visual aid because the axis would be too tall if we were to actually represent that distance.
Yeah, the paper's not long enough.
Exactly.
I mean, you need something like the size of the Empire State Building to those upper. Yeah, it's interesting. I was talking to Ryan McCreary. He's at Boys Town, and his whole thing was also talking about how those divisions of mild, moderate, and all of that. Somebody just kind of took the numbers and broke it up, but they don't actually represent function. So they're finding people at the lower part of normal, 15 to 25 dB are actually having marked functional impact. So it's kind of interesting that we've all kind of, I can tell you from a physician point of view, we've just kind of integrated into our discussions with patients, like, well, you're less than 25 dB, you're normal. And it really isn't normal. It's just somebody divided it up and said, well, we'll make 0 to 25 normal.
And I think, we're seeing more and more work come out relative to the synaptopathology and some of the other things that we're seeing now that are helping us explain why somebody might have a normal looking pure tone audiogram, but still experience significant difficulty when trying to understand speech in a competing environment, even if it's not that loud. It's that signal to noise ratio is difficult for folks, even if they have what looks like a normal audiogram. And that's one of the challenges is, it's hard to fit a hearing aid when that's the issue, because they're still primarily amplification devices. And it's not so much that making things louder is really going to help someone when it's that differentiation between speech and noise that's the problem.
Yeah, it's almost like athleticism. I think that there are some people whose brains are better at it than others.
Absolutely. And there are, types of trauma that show up differently. I mean, we see in a lot of veterans who may or may not even qualify for amplification, but they have significant auditory impairment because, even at reasonable levels, they have a very difficult time extracting speech of interest from noise of non-interest and tinnitus concerns and things like that. It's not all captured very well with that pure tone audiogram.
Is that from concussive forces or?
I think so. It can be, blast effects or even just physical trauma. Concussions being thrown from vehicles and things like that.
Yeah, the brain's not designed to be shaken or not.
No, it's really not.
Really not. And so, and I think you're, one of the things that is fascinating to me is how much more important progressing in my career that functional testing has become so much more important. I've really realized that the audiogram is just kind of the beginning. I tell patients the audiogram is like the EKG and the functional testing is like the stress tests of the heart, right? Like it's really trying to figure out how you're functioning.
And it's, related to that where I have taken some work is, taking that functional testing with an eye to how can we make sense of the data, taking that functional testing out into the real world where people actually want to be able to hear. So how do I fit someone with some technology, have them go about their typical daily life, and how can I determine whether they're doing better, worse, the same, whether, they are feeling more confident, whether they're actually objectively hearing better? How do you capture that in a data format that lets you make some recommendations, conclusions, and draw some inference from that type of investigation? And it's not easy to do.
How do you do that?
Well, one of the most promising things now is, adaptations of ecological momentary assessment. So now that everyone is walking around with a smartphone, and those smartphones can be connected to technology, so ear level technology, we're better able to set up, basically have people be walking experiments, because if their environment changes or their listening device suspects the environment changes, we can prompt them on their phone to answer some questions for us. So it seems like things just got louder. Is that correct? And that's a way of gauging whether your signal processing and acoustic analyzer in the listening device, whether that's accurate or not, or help you calibrate it to, human perceptual experience. Or we can ask, are you engaged in a conversation right now? With how many people? How would you say you're doing? Or we can set up a phone to present some speech stimuli when the devices themselves or the phone thinks it's in some background noise. We can do some mobile speech-based testing and have them respond either visually or verbally and repeat back or mark which words they've heard in a presented utterance. So with the advancements in technology, our ability to really accelerate development and assessment simultaneously has become much easier and much more accessible.
That's really cool. I mean, that's great stuff, right? So it's basically, in situation testing or in situation querying of the patient. That's really cool.
And it gives us a lens into how these things are working outside of the booth. I haven't worked clinically for a very long time, but I do recall many patients always saying, I do well with the beeps and in the sound booth, but the only time I'm in the sound booth is when I'm here for my appointment. So how,
it's almost
how helpful is that?
Say that, right? They all say, "Oh, I do great." I mean, one of the sources I think of hearing aid dissatisfaction is poor counseling when people that's not explained to them. Like, look, we're doing this in a booth. When you go outside, you should expect it to be more difficult. And that's really where we want you to assess your hearing performance. And some people will say, well, I got it and I couldn't hear. I heard at the office, but then as soon as I left, it never worked well. And that was a counseling issue too, to some extent.
Yep. I think it's identifying and kind of anchoring those expectations, I think is a very important piece. There's, we're not yet at the point, although, who knows what the next few years will hold. We're just not at the point where, we have a full on, completely artificially intelligent ear level device that will solve all of these problems for us. So we still have that, the actual human intelligence component to educate and train.
Yeah, that's interesting. I mean, when you say that artificial intelligence, will they be networked to be able to utilize some sort of algorithms outside of the device itself?
I think that's one possibility, and we're seeing some great advancements in the ability to use things like deep neural nets to extract speech of interest, or to even try and decode and understand what people are trying to pay attention to. We're still a little ways away from being able to run that on a small ear level device powered from a tiny battery.
Right.
But in offline processing or even in phone-based algorithms, we're seeing some great progress in those areas.
No, that's great stuff. So one of the things I wanted to ask you about, I was looking on your website, and you speak passionately about Bayesian hierarchical models. So can you help the listeners to explain that and understand and when they're used?
Certainly. I think so. To contextualize, depending on people's familiarity and what's kind of happening in the analysis world right now, there's over the last probably 10 years or so, mixed models have become more common in the literature across a number of different fields. Mixed models are just a way of introducing some what's referred to as varying or random effects. And so what we're really doing with these, and mixed model is kind of the same term, it's synonymous with hierarchical model, where we have a group of individuals and we want to treat each of those individuals as an individual, but also have the estimates for that individual's performance influenced by the group level performance. And so probably the best way to maybe explain this is in something like testing speech recognition with an omnidirectional microphone versus a directional microphone. And so, kind of the older school way of doing that is you say, take a group of 10 people, you test them and find their level, their SNR for 50% correct with an omni mic. Then you test that same group of people with a directional mic and find their SNR for 50% correct that way. And then you take the average in omni, the average with the directional, and see if they're different. The challenge there is that humans just really aren't carbon copies of one another. And hearing impaired listeners, even less so. We see a lot of varied performance, even in a group of people with, if you can imagine a group of 10 people with exactly the same audiogram, their performance on a speech test is likely to be very different, and their benefit from a directional mic is also very likely to be different from one another. So what a hierarchical model does is essentially treat each person as their own control. So I take subject A, I look at their performance with omni, and then I test that subject again and look at their performance with directional microphone technology. And it's that difference for that person that I'm interested in. And so I do consider the whole group performance, but I'm also looking at that individual benefit. And that is why this technique is so powerful. Now, the other distinction between what I do and what is, or at least historically has been more conventional, is that I do things under a Bayesian framework versus a frequentist framework. A Bayesian framework is really just looking at the most likely or most probable solution to a statistical problem. So the most likely answer for the benefit of a directional microphone is around 5 dB. So you'll see an improvement of 5 dB in your signal to noise ratio required for 50% correct. So if with an Omni microphone, you're getting 50% correct at 5 dB, you're likely to be getting 50% correct at 0 dB with a directional mic. The difference is that in a Bayesian system, we are assuming and treating the data that you collect as the ground truth. And so it's kind of, to put it in maybe more accessible terms, a Bayesian looks at a statistical approach and says, what is the probability that I have the right model given these data? The frequentist approach, which is what you'll see with t-tests or analysis of variance, is more, how likely are these data given that my model of no effect is true? And that's kind of what made me change my direction several years ago, is that understanding in the frequentist paradigm that you're assuming no effect and seeing if your data are unexpected given that there's no effect. And as somebody who's been in research for quite a while, I would never really design a study to look at something I thought had no effect. And so why would I model my data as though there's no effect there? Instead, I say, based on the literature, it looks like a reasonable range of effects for directional mics is, somewhere between 2 and 6 dB. And then I look at the data to tell me, does my model kind of fit with that, or should I, fit a different model that is a better fit to those data? But I look at the responses I get from people as that ground truth, and I question my model versus I trust my model and question the data that I got from people.
So let me see if I'm understood. So the old model was there's no effect, and we're going to measure the change from no effect to effect. And the model you're talking about is we're measuring the change in effect, assuming there is a baseline effect in each individual, and kind of controlling out the other things. So for instance, hearing is a lot more than just your ears. It's all this other stuff. But if you see the change in each individual, then you've almost controlled for that other stuff, whatever that other stuff is. Am I getting that right?
You're getting it exactly right. It's just that. And some of these models can get pretty complex, but it's that complexity and flexibility that I have found generally just necessary. If, I don't know how often people look at the underlying assumptions of some of the typical statistical tests that we do. But what I found when trying to model more complicated data, especially with hearing impaired individuals, I found that in trying to find the right statistical test, I was never really meeting any of those assumptions. And the models were assuming a lot of things that I just couldn't assume about my data. So I needed to find a way to be more flexible and build things essentially from scratch and customize what I know about the data and what I know about the technology, and analyze those data in a way that speaks to the true nature of how those data are generated or created. And so it's become, it's very fun. It's challenging. And I find that, it gives you estimates of uncertainty, which is also something that's lacking in the frequentist paradigm. And when we're thinking about technology development or benefit from technology, or even just how someone performs on a self-assessment, a listening confidence questionnaire or something like that, conclusions should always, in my opinion, come with your uncertainty about that conclusion. So if I say a directional mic will give you 5 dB of benefit, but that's plus or minus 2 dB. So that is the very important piece, because it really depends on the individual and how precise is my estimate. So if I can say that you'll see 5 dB of benefit with a directional mic plus or minus 0.5 dB, then you can really expect a noticeable effect. But if that confidence is, 5 dB of benefit plus or minus 3, well, then some people might notice a lot, but others might not notice anything at all. And that is something to be aware of in counseling a patient and setting those expectations, or if you're in early stages of development, being able to weigh out whether or not your eventual end user is going to notice, appreciate, and gain maximum benefit from that technology. So having that estimate of uncertainty is really an important piece of both clinical understanding as well as industry-based technological development.
Yeah, it's interesting because what I would tell you is the clinical context of what you're talking about is kind of something I talk about with patients, and that's what I always say. Hearing's not just your ears; it's your brain, right? And so you're trying to measure the incremental change of some system change, omni to a directional microphone or something like that, and you've got all of these other aspects that are vary from patient to patient, so you can't put everybody in the same bucket and say, well, we saw an overall improvement in this group. We need to look at each person because some of them are, going back to the athletic analogy, some of them are, highly athletically impaired, and some of them are the LeBron James of hearing. And so, if you put both of those people in a group, that LeBron James might, skew the whole group. And so you're kind of controlling for that.
Exactly.
That's really interesting. And so, is this commonly used in the hearing science space or no?
It's less so in the hearing science space, but it's becoming more prominent. There is a large community in the psychology space. I think motivated significantly by some of the replication crises and some of the challenges that have happened in the psychology literature. There's been a noticeable shift in folks using a Bayesian paradigm that makes things a little bit more robust, a little bit more repeatable, and gives you these estimates of uncertainty and what to expect. And so we're seeing it. I think one of the major challenges, so Bayesian inference and analysis predates all of frequentist stuff. So, the Bayes theorem goes back to 1862. It's been around a very long time. It just hasn't been really approachable or accessible until now, when we have very affordable computing platforms.
Right,
so
the power to do it, right?
The power to do it. I mean, some of the models I fit now would have taken, a room full of mainframes and a month to do, 20 years ago. Now, with some of the fantastic developments in computing languages as well as hardware that you can have in your home, I can run a model in a couple of hours or a day that just previously would not have even been approachable at all. And so one of the things to be aware of is just that now we can. So I think we've known for a long time that this form of analysis and inference
just wasn't practical,
although powerful and entirely enviable. It just wasn't approachable or possible. And now it is.
When computations were done by computers that were human beings, right?
Exactly.
Getting 1,000 people to do calculations for several weeks to do one of these was a huge investment of resources that couldn't afford.
And to try and contextualize that, the language that I use, it's called STAN. It became public in 2013, so it's
really new.
It really hasn't been around that long, and right. So it's at the leading bleeding edge of things, and it's informed by a large community of computational statisticians, and we've got a lot of power here, and it's really an exciting time to be doing this kind of work.
I really have to talk to you if I'm going to do any studies in the near future. That's for sure.
Happy to.
Yeah. So I know this is kind of, so what other measurements in audiology do you think are kind of cool or interesting or hard to communicate?
Well, I think, some of the challenges come from a lot of terms used interchangeably that probably aren't strictly interchangeable when we talk about speech discrimination, speech recognition, or word understanding. We don't really have a lot of clinically used
presentation, right?
We don't, and some of these things are measurable, but what we're calling a discrimination task isn't necessarily discrimination. Discrimination kind of implies selecting the correct choice out of a fixed set of given choices. And so word discrimination would be, I say a word, which one of these was it? But we actually use that term to describe an open set word test. So we'll present a word and someone takes, either a guess or heard that word. It's not really discriminating between things. It's typically also not understanding.
It's determinative, right?
It is.
Right. Interesting.
And, we're not asking if they've understood the word or what it means. We're asking, it's identify. So it's word identification or recognition. And I think that's a bit of a challenge. And especially when, if we're counseling a patient and we talk about speech understanding, again, kind of linking back to the expectations. Well, you said my speech understanding was very good, but I go home and I can't understand anything people are saying. And so there's this mismatch. And so, you can identify words, but stringing them together amidst some noise and making sense of a whole paragraph is a different thing than correctly identifying a word that you heard, even if it's presented in some noise. And I think
or even more subtly getting a pun or a joke.
Exactly.
Right. Which is even way more complex than just, I understand what somebody's saying. It's that hearing impaired person who is listening to the conversation and then you can see they're processing it. And then 45 seconds later, they kind of chuckle because they actually finally put the joke together. And that's not because they don't have the horsepower. It's because they're working so hard to communicate. So.
And that listening effort piece is a challenge. I've done some work previously trying to find ways to, best identify or at least find some kind of indexing into what we might call listening effort. And I've looked at this through pupillometry, through EEG measures, through reaction times. And all of these things give us different and often not even correlated measures of what's happening. So I think when we try to speak to patients or researchers about listening effort, it puts the onus on us to explain what exactly it is we're referring to with effort.
Yeah, well, because communication is so complex, hearing is obviously one of the entry gateways into it, but obviously there's so much more to it, just even within different languages, how ideas are expressed. And I mean, look, philosophers spend all of their time, defining terms to use language to be able to communicate complex ideas that are very hard to grasp. So it's a challenge. So it's fascinating stuff. It really is. Thank you so much. So, one of the questions I like to ask is, who do you thank in terms of your career? Who are those people who had a great impact on you along the pathway? Who are those people?
I've had a number of fantastic colleagues and mentors. There's a fantastic hearing scientist named Christophe Michel, who first introduced me to Bayesian inference and kind of set me down this path. One of my favorite quotes from him was, I think I asked, well, why would you use a Bayesian model over something else? And his response to me was, well, if you care about what your data have to say and why you collected them, then you would use a Bayesian model. If you don't, then I guess you could use something else or basically say, not do the study.
you silly person, this is the way to do it.
Exactly. And so that lit a fire under me that just set me down this path several years ago. I've seen some fantastic leadership through individuals like Brent Edwards and Simon Carlisle, who were just exemplary leaders for teams that I was a part of. Both of them, showed me a path to team leadership that embodies, philosophy of science as well as philosophy of leadership. And those two gentlemen were just fantastic influences on me. And probably my most significant resource for thinking through science questions and the lens upon which we look at the world is my significant other, my wife, Stella Ng, who is an education researcher at the University of Toronto. She is an absolute phenomenal and qualitative inquiry expert. And the way she approaches her research questions and the rigor that she embodies in asking really difficult questions and coming up with really interesting answers has informed a lot of what I do. Although I'm quantitative, The way that I think through questions and seek to answer them is highly influenced by the way that she approaches her work.
That's awesome. I'm sure dinner time conversation is fascinating.
Yeah, well, for us, I mean, I think probably guests would be maybe less thrilled, but we spend a lot of our time talking science in our house.
That's great. That's great. Well, everybody, we've been having a great conversation with Dr. Jeff Crukley. Jeff, where can people learn more about you?
So I have a website, jeffcrukley.com, jeffcrukley.com. And I have contact information there, as well as some examples of previous projects and some presentations I've given. And I'm happy to chat anytime.
Well, thank you so much for coming. This has been great. I really appreciate your time and really interesting. Thanks so much.
Thank you very much, Mark.
Thanks for tuning in to the Listen Up podcast. We'll see you again next time, and be sure to click subscribe to get updates on future episodes.